In chemistry, an ionic compound is a chemical compound in which ions are held together in a structure by electrostatic forces termed ionic bonds. The positively charged ions are called cations and the negatively charged ions are called anions. These can be simple ions such as the sodium and chloride in sodium chloride, or polyatomic species such as the carbonate ion in calcium carbonate. Individual ions within an ionic compound usually have multiple nearest neighbours, so are not considered to be part of molecules, but instead part of a continuous three-dimensional network, usually in a crystalline structure. Ionic compounds typically have high melting and boiling points, and are hard and brittle. As solids they are almost always electrically insulating, but when melted or dissolved they become highly conductive, because the ions are mobilized. Ionic compounds without the acidic hydrogen ion, or the basic ions hydroxide or oxide, are also known as salts and can be formed by acid-base reactions. Ionic compounds containing hydrogen ions are classified as acids and compounds containing hydroxide or oxide ions are classified as bases. History of discovery. The word ion is the Greek a 1/4 degree I y 1/2, ion, going, the present participle of a 1/4 degree I 1/2 I plus or minus I to the first, ioni, to go. This term was introduced by English physicist and chemist Michael Faraday in 1834 for the then unknown species that goes from one electrode to the other through an aqueous medium. In 1913 the crystal structure of sodium chloride was determined by William Henry Bragg and William Lawrence Bragg. This revealed that there were 6 equidistant nearest neighbors for each atom, demonstrating that the constituents were not arranged in molecules or finite aggregates, but instead as a network with long-range crystalline order. Many other inorganic compounds were also found to have similar structural features. These compounds were soon described as being constituted of ions rather than neutral atoms, but proof of this hypothesis was not found until the mid-1920s, when X-ray reflection experiments were performed. Principal contributors to the development of a theoretical treatment of ionic crystal structures were Max Born, Fritz Haber, Alfred Landau. Copyright, Erwin Madelung, Paul Peter Ewald, and Kazimierz Fajans. Born predicted crystal energies based on the assumption of ionic constituents, which showed good correspondence to thermochemical measurements, further supporting the assumption. Formation. Ionic compounds can be produced by evaporation, precipitation, or freezing. If the solvent from an electrolyte solution is evaporated, the ions do not go into the vapor, but stay in the remaining solution, and ultimately crystallize into the ionic compound. Insoluble ionic compounds can be precipitated by mixing 2 solutions, one with the cation and one with the anion in it. If the 2 solutions have hydrogen ions and hydroxide ions as the counterions, this is called an acid-base reaction. Molten salts will solidify on cooling to below their freezing point. Bonding. Ions in ionic compounds are primarily held together by the electrostatic forces between the charge distribution of these bodies, and in particular the ionic bond resulting from the long-ranged Coulomb attraction between the net charge on anions and cations. When a pair of ions comes close enough for their outer electron shells to overlap, a short-ranged repulsive force occurs, due to the Pauli exclusion principle. There is also a small additional attractive force from van der Waals interactions which contributes only around 1 to 2% of the cohesive energy for small ions. The balance between these forces leads to a potential energy well with a minimum energy when the nuclei are separated by a specific equilibrium distance. If the electronic structure of the 2 interacting bodies is affected by the presence of one another, covalent interactions also contribute. Ionic compounds are rarely purely ionic, that is held together only by electrostatic forces. The bonds between even the most electronegative electropositive pairs such as those in cesium fluoride exhibit a small degree of covalency. Conversely, covalent bonds between unlike atoms often exhibit some charge separation and can be considered to have a partial ionic character. The circumstances under which a compound will have ionic or covalent character can typically be understood using HSAB theory, whereby the compounds with the most ionic character are those consisting of hard acids and hard bases, small, highly charged ions with a high difference in electronegativities between the anion and cation. This difference in electronegativities means that the charge separation is maintained even when the ions are in contact. Structure: ions typically pack into extremely regular crystalline structures, in an arrangement that minimizes the lattice energy. The lattice energy is the summation of the interaction of all sites with all other sites. For spherical ions only the charges and distances are required to determine the interaction energy. For any particular crystal structure, all distances are related to the smallest internuclear distance. So for each possible crystal structure, the total Coulomb energy can be related to the Coulomb energy of unit charges at the nearest neighbor distance by a multiplicative constant called the Madelung constant that can be efficiently computed using an Ewald sum. When a reasonable form is assumed for the additional repulsive energy, the total lattice energy can be modeled using the Born-Lambda copyright equation. Using an even simpler approximation of the ions as impenetrable hard spheres, the arrangement of anions in these systems are often related to close-packed arrangements of spheres, with the cations occupying interstices. Depending on the stoichiometry of the ionic compound, and the coordination of cations and anions, a variety of structures are commonly observed, and theoretically rationalized by Pauling's rules. In some cases the anions take on a simple cubic packing, and the resulting common structures observed are, some ionic liquids, particularly with mixtures of anions or cations, can be cooled rapidly enough that there is not enough time for crystal nucleation to occur, so an ionic glass is formed. Properties: melting and boiling points equals, electrostatic forces between particles are strongest when the charges are high, and the distance between the nuclei of the ions is small. In such cases, they generally have very high melting and boiling points and a low vapor pressure. Inorganic compounds with simple ions typically have small ions, and thus have high melting points, so are solids at room temperature. At high temperatures ionic solids melt and become molten salts. Some substances with larger ions, however, do form ionic liquids at room temperature. Brittleness equals, ionic compounds are typically very brittle. Once they reach the limit of their strength, they cannot deform malleably, because the strict alignment of positive and negative ions must be maintained. Instead the material undergoes brittle fracture. Solubility equals, when ionic compounds dissolve, the individual ions dissociate and are solvated by the solvent and disperse throughout the resulting solution. The solubility is highest in polar solvents or ionic liquids, but tends to be low in nonpolar solvents. This is principally because the resulting ion-dipole interactions are significantly stronger than ion-induced dipole interactions, so the heat of solution is higher. When the oppositely charged ions in the solid ionic lattice are surrounded by the opposite pole of a polar molecule, the solid ions are pulled out of the lattice and into the liquid. If the solvation energy exceeds the lattice energy, the energy released in solvation is used to overcome the lattice energy so that the ions are freed from their positions in the crystal and dissolve in the liquid. Because the ions are released into solution when dissolved, soluble salts are a common class of electrolytes. Electrical conductivity equals, although ionic compounds contain charged atoms or clusters, these materials do not typically conduct electricity when the substance is solid. In order to conduct, the charged particles must be mobile rather than stationary in a crystal lattice. When the ionic compounds are dissolved in a liquid or are themselves melted into a liquid, they can conduct electricity because the ions become mobile. In some unusual ionic compounds, fast ion conductors, and ionic glasses, one or more of the ionic components has a significant mobility, allowing conductivity even while the material as a whole remains solid. Color equals. The color of an ionic compound is often different to the color of an aqueous solution containing the constituent ions. The anions in compounds with bonds with the most ionic character tend to be colorless. In compounds with less ionic character, their color deepens through yellow, orange, red and black. The absorption band of simple cations shift toward shorter wavelength when they are involved in more covalent interactions. This occurs during hydration of metal ions, so colorless ionic compounds with anion absorbing in the infrared can become colorful in solution. Uses: Ionic compounds have long had a wide variety of uses and applications. Many minerals are ionic. Humans have processed sodium chloride for over 8,000 years, using it first as a food seasoning and preservative, and now also in manufacturing, agriculture, water conditioning, and for de-icing roads. Nomenclature. According to the nomenclature recommended by IUPAC, ionic compounds are named according to their composition, not their structure. In the most simple case of a binary ionic compound with no possible ambiguity about the charges and thus the stoichiometry, the common name is written using two words. The name of the cation comes first, followed by the name of the anion. For example, MgCl2 is named magnesium chloride, and now 2SO4 is named sodium sulfate. To obtain the empirical formula from these names, the stoichiometry can be deduced from the charges on the ions, and the requirement of overall charge neutrality. If there are multiple cations and/or anions, multiplicative prefixes are often required to indicate the relative compositions, and cations then anions are listed in alphabetical order. For example, KMgCl3 is named magnesium potassium trichloride. When one of the ions already has a multiplicative prefix in its name, the alternate multiplicative prefixes are used. For example, Ba, BrF4, 2 is named barium bis, tetrafluoridobromate. Compounds containing one or more elements which can exist in a variety of charge oxidation states will have a stoichiometry that depends on which oxidation states are present, to ensure overall neutrality. This can be indicated in the name by specifying either the oxidation state of the elements present, or the charge on the ions. Because of the risk of ambiguity in allocating oxidation states, IUPAC prefers direct indication of the ionic charge numbers. These are written as an Arabic integer followed by the sign in parentheses directly after the name of the cation. For example, FeSO4 is named iron 2 plus sulfate, whereas Fe2, SO4, 3 is named iron 3 plus sulfate. Stock nomenclature, still in common use, writes the oxidation number in Roman numerals. So the examples given above would be named iron 2, sulfate and iron 3, sulfate respectively. An even older naming system for metal cations, also still widely used, appended the suffixes -us and -ic to the Latin roots the name, to give special names for the low and high oxidation states. For example, this scheme uses ferrous and ferric for iron 2 and iron 3, respectively, so the examples given above were classically named ferrous sulfate and ferric sulfate. See also, IUPAC nomenclature, bonding in solids, solubility. References. Bibliography Ashcroft, Neil W. Mermin, N. David. Solid-state physics. New York, Holt, Reinhardt and Winston. ISBN 0030839939. Brown, Theodore L. LeMay, H. Eugene, Jr. Burson, Bruce E. Lanford, Stephen. Sagatis, Delius. Duffy, Neil. Chemistry, The Central Science, A Broad Perspective. Frings Forest, NSW Pearson, Australia. ISBN 9781442511477. International Union of Pure and Applied Chemistry, Division of Chemical Nomenclature. Neil G. Connolly, ed. Nomenclature of Inorganic Chemistry, IUPAC Recommendations 2005. Cambridge, RSC Pub. ISBN 0854044388. Kittle, Charles. Introduction to Solid-State Physics. Hoboken, New Jersey, John Wiley & Sons. ISBN 0471415226-X. Macquarie, Donald A. Rock, Peter. A General Chemistry. New York, W. H. Freeman & Company. ISBN 0716721694. Pauling, Linus. The Nature of the Chemical Bond and the Structure of Molecules and Crystals, An Introduction to Modern Structural Chemistry. Ithaca, New York: Cornell University Press. ISBN 0801403332.